introduction. I'm Jonathan Marin. I'm a first-year PhD student at the University of Strathclyde in Glasgow, and I am here today to speak on behalf of the whole team of this research. And today I'm going to talk about the structural steel crack propagation experimental and numerical analysis. So, as a brief outline, we're going to talk about the background of the project, methodology, some experimental setup, also numerical setup, as well as some results that we got so far, and finally the discussion and conclusions. So, as a background, usually as engineers we tend to face very challenging projects where sometimes it's kind of difficult to predict loads. And therefore, we would like to perform certain kind of analysis to improve the structural integrity of certain components. So, therefore, the design assessment of certain parts is required, right? So, in order to produce or to generate this kind of analysis, we need to rely on certain kind of data, which sometimes is not available on literature, such as fatigue and fracture data, and this is something that needs to be studied further. And also we can use certain tools such as computer-aided engineers tools such as FEA or another kind of methodologies. And if we look at some certain materials, we can find certain guidelines or certain standards that they provide some insight of how you can provide this material data, but sometimes fatigue and fracture is not addressed. So this is something that needs to be studied further. So in this case, we can investigate the material properties of these materials using certain tools such as ANSYS Smart Tool or Abacus XFEM. So the methodology applied for this project was as follows. First, we performed an experimental analysis using the ASTM E647 procedure, where in first point we got the material data using the CMOD compact tension test procedure. Then we performed some numerical analysis using the ANSYS Smart Tool test, using the compact tension test, as I said before, in order to first estimate the parameters used that are used in the compliance of the test of this compact tension test. So then we perform the processing of these materials in order to refine the parameters of the Paris law. And finally, then we introduce those parameters within the ANSYS Smart Tool in order to make a comparison between these material properties updated with the sample test that we performed. So here are some of the setup parameters that we use for this lab test. We used a sample of a width of 40 millimeters with a notch of 10 millimeters. And we used the instance machine with a mean load of 4.5 kilonewtons and a load amplitude of 4.5 kilonewtons as well. So, as I said before, our study was based on the ASTM E647 procedure. Here, one of the things that I'd like to highlight is that we use a load range of 9 kilonewtons, as I said before, and a load ratio of 0. Also, the idea here is try to obtain the stress intensity range using this methodology in order then to get the parameters for the Paris law. Well, the ASTM E647 gives you this this expression in order to calculate the stress intensity factor, right? According to the compliance of the test. And for this analysis, we use the front face compliance, where we measure the CMOD, the crack mouth opening displacement, in order then to determine the Paris law coefficients. So this is something that I mentioned earlier. The procedure gives you this equation in order to calculate the crack opening, right? Considering the CMOD, but these coefficients are based in certain parameters of the sample. So this was our first point of start, where we performed an analysis using ANSYS Smart tool, where we could adjust these parameters according to our sample dimensions. So this is some of the setup of the numerical analysis. We use a solid model where we model just the half of the of this sample. This sample because it's symmetric, right? So in order to save certain computer time, we could perform this kind of analysis. And here are some of the results that we got according to the coefficients, in order to adjust this coefficient and get the crack growth parameters, so then we can perform, and then we can get the stress intensity factor range. So here you can see that they are slightly different compared to the ones that are provided by the procedure. So this gives us more accurate results. And here are some of the results for the 3 specimens that we tested. First one, we tested grade 1. We decided to call it grade 1 because it's something that we cannot disclose so far. But what we can tell is that it has a yield strength of 235 megapascals. And here you can see some of the results regarding the crack length against the number of cycles. And then we try to get try to plot the Paris curve using this procedure, but for this kind of material, we got a certain kind of noisy data, so we're trying to find out what was going on, and if there is something wrong regarding the setup of the machines. So this is something that we are still working on. But then we got the data for the second steel, which is a grade 2. And here, well, again, the same results as shown before, but here we can get a more stable data for the Paris law curve. Still, we've got some noisy at the very beginning of this test, so this is something that we are still working on as well. Sorry, I think yeah, this is a grade 3, and this is what I was mentioning earlier. Well, this is the data that we got from the finite element analysis using the SMART tool for the 3 sample data that we got. And here are the crack length regarding the cycles of data. So to do this, we use some estimated parameters instead of using the ones that we got from the lab test, but then we're going to adjust accordingly these graphs. So here are some of the results for the Paris law for the 3 samples, and as you can see here, there are a little bit of noise, especially for the grade 1 material, which is the in color blue, or the 255 megapascals in unit strength. Well, we perform the regression in order to get the Paris law parameters, and then this is something that we applied within the ANSYS Smart tool using the coefficients adjusted for the to calculate the stress intensity factor according to the standard, but as well we use the parameters of the Paris law to perform this analysis. And here is something that we can highlight, that the stress intensity factor goes between 23 and 26 megapascal square root of meter, which is something a little bit similar of what we got in the beginning of the sample data, such as the grade 3 in this case. So sorry for scrolling up. Well, this is some of the results comparing the lab test results against the final element analysis using the updated parameters for the Paris law. And here we can see that using the final element analysis, we have certain differences, but the final element analysis seems to be a little bit more conservative compared to the experimental data. So, well, this is just to show you some of the videos that we took during the procedure. I guess that most of you are familiar with this kind of stuff. So, as a conclusion and discussion, we were able to perform the analysis using the ANSYS Smart tool in order to update the parameters of the compliance relationship. We were able also to study these three samples or these three steel grades. Also, some of important thing to highlight is that still we need to improve some of the setup parameters of the machines, because we, as you could see, that we got some noisy data during the first stages of the test. So that seems that we need to perform a long test in order to smooth these results. Basically, the idea of this research, of this study, is that then we can apply these parameters or this data to perform certain kind of analysis and improve machines such as a bucket excavator, as you can see here. So, well, that brings me almost to the end of this presentation. So thank you all for your attention, and thank you.
So, are there any questions? Okay, we got here just one question. When you determine the values of Paris coefficients, C and M, I think this tells it.
Yeah.
C was like something to the power of minus 27.
Yeah.
It's very, very, that would give billions of cycles.
Yeah, exactly. It's well, it's because it's in meters.
You use meters instead of
pascals.
millimeter.
You see, yeah.
Right.
Pascals, yeah, it's a kind of a strange, but
usually
you see that in megapascal square.
Yeah, I thought that was something. I know that ANSYS by default uses the megapascals.
But if you take a look at M, well, it has some values that are similar to other kind of steels. So
yes, that's usually similar. Although every piece of steel you investigate for Paris coefficients, you're always going to get something different.
Yeah, exactly.
Unavoidable. My PhD wasn't something similar, actually.
Thank you.
Okay. Thank you.
Just a comment, because you remind me some time ago, and in my time I was not able to use this compliance technique. I was forced to observe the grades.
Oh.
With microscope, but it is a good way to start because you avoid some uncertainty from calibrations and maybe this scatter will be solved because it is not typical. So maybe I recommend look the correct.
To look at, to go to the microscope. Yeah, it's something that probably we should do. And yeah, the idea was first try to avoid that process.
Yeah, it's time consuming, but
It's time consuming.
it's a way to be sure
Exactly.
and to calibrate to confirm that you are doing the right calibration. It's complex.
Thank you.
Okay, thank you.
Thank you.
Then